All right, today we are going to be talking about second order filters, or RLC filters. So we are going to focus today on what are called band pass and band stop filters, but I am going to introduce second order low pass and high pass filters and give you a little bit of information on them. So if we have the following circuit, R, here's j omega L, here's 1 over j omega C. Here's our input signal, Vn, as a function of frequency. Here's where we take our output voltage, V out, as a function of frequency. Just based on this, what kind of filter do you think this is? All right. Anybody care to venture a guess?
Since the inductor is first, it's more similar to like a low pass, and since the capacitor is in the middle.
All right, so we're taking the output voltage over the capacitor by itself, right? So at very low frequencies, the capacitor is going to look like an open circuit, meaning we should see most of the signal pass through. Some of it might roll off because the inductor is going to start increasing in impedance as frequency goes up. At very high frequencies, the capacitor is going to look like a short circuit and our output voltage is definitely zero. So this is an example of a second order low pass filter. All right. So I'm just going to say that it's a low pass filter. By inspection, we can develop a relationship for the transfer function. It's going to be 1 over j omega C divided by R plus j omega L plus 1 over j omega C. And just doing the very small amount of complex algebra, this comes out to be 1 over 1 plus omega squared LC plus j omega RC. Not going to give you guys an equation for the frequency response or the phase response because you can get it from this fairly easily. I will tell you, however, that the 3 decibel cutoff frequency omega C is 1 over the square root of LC. So if I give you guys a homework problem, I feel like that's probably enough information on there. So moving along, we have the exact same circuit, except we switch the positions of the capacitor and the inductor. Oops, except that I'm not switching their positions. Here's R, here's j omega 1 over j omega C, here's j omega L, here's our input signal Vn of omega, here's our output V out of omega. So if the first one was a low pass filter, then this one has to be the high pass filter. Because it has an inductor at the output for very low frequencies, the inductor looks like a short circuit. So everything is attenuated. At very high frequencies, the inductor looks like an open circuit. So everything is passed. So this is a high pass filter, HPF. It has a transfer function of H of omega is equal to J omega L divided by that same denominator, R plus J omega L plus 1 over J omega C. And when we multiply through by a factor of J omega C, we get omega squared LC in our numerator, and our denominator becomes 1 plus, goodness, omega squared LC plus J omega RC. Again, we will have a 3 decibel cutoff frequency of 1 over the square root of LC. All right, so we talked a whole heck of a lot on Wednesday about low pass filters and high pass filters. So now we're going to get into our types of filters that we can only recognize with second order or higher circuits. So let's take a look at this guy. And we're actually going to go through the analysis for him. So here is our input, Vn as a function of omega. Here is our output, Vout as a function of omega. Sorry, that is obviously an inductor. So we have J omega L. Here is 1 over J omega C. And now we're taking our output over our resistance. Okay. So by inspection, what is our transfer function for this guy going to be? Since it's a passive filter, we can just use simple voltage division like we've been doing. So it's a voltage drop over the resistor, which means the resistance impedance is going to be in the numerator and the total series impedance is going to be in the denominator. So it's going to look like R over R plus J omega L plus 1 over J omega C. And when we multiply through by a factor of J omega C over J omega C, we get in the denominator 1 plus omega squared LC plus J omega RC. And in our numerator, we are going to have J omega RC. So this is our transfer function. To get our frequency response and phase response, we're going to have to get this guy into a rectangular form. So that means I'm going to multiply this by 1 plus omega squared LC minus J omega RC. So I'm multiplying by the complex conjugate of the denominator over the complex conjugate of the denominator. And this is going to give me, let's do it down here. Let's see what's happening here. So we're obviously going to have in the numerator a factor of J omega RC times 1 plus omega squared LC. since that has the j, that's going to be the imaginary part. We're also going to have negative j omega RC times positive j omega RC, which is negative j squared, or positive 1 omega RC quantity squared plus j omega RC times 1 plus omega squared LC. And our denominator is going to be 1 plus omega squared LC quantity squared plus omega RC quantity squared. All right. Anybody got any problems with my complex algebra there? Everything seems on the up and up. Okay, so to take the magnitude h of omega we are going to have the square of the real part. So that's 1 plus omega squared LC quantity squared plus omega RC quantity squared down here. Up here we have omega RC quantity squared. We square this whole thing. Then we put in our imaginary part. So doing the denominator first, 1 plus omega squared LC quantity squared plus omega RC quantity squared. And then up here, we are going to have omega RC times 1 plus omega squared LC. This whole thing squared. And let's see what's going on here. So on the real part, I have omega R in my numerator, I have omega RC quantity squared, and then that is squared. So I'm going to have a factor of omega RC squared to the second power. On my right-hand side, for the imaginary part, I'm going to have omega RC, that bit is squared. And so I'm going to have a common factor of omega RC squared on both sides, right? So I'm going to have omega RC squared times 1 plus omega squared LC squared plus omega RC squared. Do you all agree with this? Let's start there. So what I am arguing is that I can square this guy and this guy. So if I squared that whole thing, I get this. So I should be able to easily see that I have a common factor of omega RC quantity squared that I can factor out. That is being multiplied by 1 plus omega squared LC quantity squared, which gives me this first term. And then it's also multiplied by a factor of omega RC quantity squared. All right. Divide this by 1 plus omega squared LC. Sorry, I didn't need to have squared plus omega RC squared squared. This guy cancels this, and we are left with omega RC divided by the square root of 1 plus omega squared LC squared plus omega RC squared. All right, so what does this guy look like when omega is 0 radians per second? Excuse me. So for very low frequencies, 0. What does this guy look like for very high frequencies? Agree. Right? So we have at a frequency of infinity, we have omega squared, so that's going to be infinity squared times some number plus 1. So it's going to look like infinity squared squared. Infinity to the 4th power. We take the square root of that, and so it's going to be infinity squared in the denominator and infinity in the numerator, which means we have 1 over infinity, approximately. So it's going to look like 0. So if it looks, if it's attenuating stuff at very low frequencies and attenuating stuff at very high frequencies, hopefully it's passing stuff in the middle. This makes this a band pass filter. Okay. This band pass filter, if you will recall, the frequency response for a band pass filter looks something like this. So this is going to be omega. This is going to be h of omega. Then let's put it in decibels. Let's not put it in decibels, actually. Since this is a passive filter, its maximum value is going to be at 1. And so what this is going to look like is something like this. Almost like a bell curve, right? Where the center frequency is the resonant frequency of the circuit. So let's talk about that real quick. This is inherently a series RLC circuit, right? Because it's got a resistor, a capacitor, and inductor in series. So when we did transient analysis, what was the resonant frequency of a series RLC circuit? Yep. And so that is the exact same thing. So we have a resonant frequency at 1 over the square root of LC. And then I'm going to put an X here and an X here. And I'm going to say arbitrarily that this is the point where our amplitude reaches 1 over the square root of 2, which means this spot corresponds to what we'll call omega low. This spot over here corresponds to what we'll call omega high, and those are both 3 decibel cutoff frequencies, okay? Omega low, not going to derive it, but it is negative R over twice L plus the square root of R over twice L squared plus omega naught squared, or plus one over the square root of LC squared. This hopefully looks pretty darn familiar, right? For a series RLC circuit, alpha was R over 2L. So this is really just giving you one of your eigenvalues, your S values, if this were an overdamped system. Omega high is going to be slightly different, okay? So when we were dealing with the transient analysis, our first natural frequency was negative alpha plus the square root of alpha squared plus omega, or minus omega naught squared. Here we have a plus sign. For our omega high, it's going to be positive R over 2L plus the square root of R over 2L quantity squared plus 1 over the square root of LC squared. So these are giving us our our high value for our 3 decibel cutoff frequency and our low value for our 3 decibel cutoff frequency. So these two frequencies defined what's called the mid-band of this guy, okay? And the mid-band is just the range of frequencies that get passed. We can say that this circuit has a bandwidth equal to omega high minus omega low, which is exactly equal to R over L. So that gives us our bandwidth. So I haven't decided if I'm going to give this to you guys as a simple project or make it a problem on your exam. But these band pass filters like this are how electronic circuits like our radios and telephones or cell phones and all that kind of stuff tune to a very, very specific frequency. And then the bandwidth tells us what range of frequencies to accept things at. So for instance, if we are talking about FM radio, who knows what the frequency is for the FM radio station here on Tech Campus? 89.1. Yeah. So KLPI, Louisiana Tech's radio station, is it's KLPI 89.1, where 89.1 is the frequency that the radio station broadcasts at in megahertz. All right. For a FM radio station, what's the closest other station? What's the closest possible other station that we could get? 89.3. Okay, so it goes 89.1 to 89.3 to 89.5, et cetera, all the way up to 107.9. I think it starts at 87.1. So we have these center frequencies of our radio band, which is the omega naught, and then the separation is provided by the bandwidth. So for an FM radio signal, we would say that the bandwidth is 0.2 megahertz, because that's the separation between the closest station. So we have a bandwidth of 200 kilohertz centered around the resonant frequency of the station that we're trying to listen to. So if you wanted to build a receiver that could pick up FM radio signals, this is what you would have to build around. You know what the resonant frequency is. You have a method to determine or set the bandwidth of your system. And from there, it's just figuring out how to move this center frequency around, which is typically done with a variable capacitor, right? Because the bandwidth doesn't depend on the capacitance at all. So if you have a capacitor that you can tune, you're able to move that center frequency around to pick up other stations while maintaining this bandwidth so that you're never getting interference from secondary signals. So that's how radios work. At least that's how the receiver portion that's connected to the antenna filters out everything except the station that it wants to pick up, I guess would be a better way. All right, so we know what the frequency response is. We know what our resonant frequencies are, our low and high cutoff frequencies. So the last thing that we have then, excuse me, is our phase response. So our phase response, theta h of omega, is the arctangent of our imaginary portion, which is omega RC 1 plus omega squared LC. Divided by 1 plus omega squared LC squared plus omega RC squared. And then we have our real part, which was omega RC squared. So obviously the denominators cancel each other, and this cancels one of those. So we're left with the arctangent of 1 plus omega squared LC divided by omega RC as our phase response. All right, so this was a band pass filter. The last thing that we're going to talk about today, looks like we're going to get out a little bit early. Oh no, it's Friday. Is the band stop. All right. So if we look through these circuits, our first one, we took the output over the capacitor and we got a high pass, or excuse me, a low pass filter. The second one, we took the output over the inductor and we get a high pass filter. What a band stop filter is effectively a high pass filter in series with a low pass filter. Okay, so it passes a certain amount of low frequency signals and then attenuates a certain range of high frequency signals until it starts passing the highest of frequency signals. So we are going to take our output for our series RLC circuit over both the capacitor and the inductor to form the band stop circuit. So here's our resistor. Here's our inductor, capacitor. So this is J omega L. This is 1 over J omega C. And our transfer function, H of omega, is the voltage drop over both the capacitor and the inductor. So that's going to be J omega L plus 1 over J omega C divided by R plus J omega L plus 1 over J omega C, multiplying through by a factor of J omega C over J omega C gives us 1 plus omega squared LC divided by 1 plus omega squared LC plus J omega RC. So that's our simplified version of the transfer function. We're going to do the exact same thing we've been doing and multiply this by the complex conjugate of the denominator over the complex conjugate of the denominator. So it's going to be 1 plus omega squared LC minus J omega RC divided by 1 plus omega squared LC minus J omega RC. And for our real part in the numerator, it's obviously going to be 1 plus omega squared LC quantity squared. For our imaginary part, we're going to have minus J omega RC times 1 plus omega squared LC. And for our denominator, we'll have 1 plus omega squared LC quantity squared plus omega RC quantity squared. So we've got this guy in a form to where we can find the frequency response. So our magnitude of this guy is then 1 plus omega squared LC quantity squared over 1 plus omega squared LC quantity squared plus omega RC quantity squared. this whole fraction squared. And then over here we have the imaginary part, so that's going to be omega RC times 1 plus omega squared LC over the same denominator, 1 plus omega squared LC quantity squared plus omega RC squared squared. And this is going to give us, we have a common factor of 1 plus omega squared LC quantity squared. Then we're going to have that multiplied by 1 plus omega squared LC squared plus omega RC squared. And down here, 1 plus omega squared LC squared plus omega RC squared quantity squared. This guy cancels out 1 power of that. And finally, we have our frequency response, 1 plus omega squared LC divided by the square root of 1 plus omega squared LC squared plus omega RC squared. All right, so to prove that this is a band stop filter, at omega is equal to 0, what does this come out to be? 1, right? Because we're going to have 1 plus 0 over 1 plus the square root of 1 plus 0 plus 0. So it looks like 1 at infinity. It's also going to come out to be 1. We're going to have infinity squared over the square root of infinity to the 4th power is infinity squared over infinity squared. And so we see that it passes low frequency signals and it passes high frequency signals. And we certainly hope that it's rejecting frequencies in the middle. So our frequency response is going to look something like this, where this is 1. This is our resonant frequency. And this frequency here will be omega low. This frequency here will be omega high, where omega low is the 3 decibel cutoff frequency for the low pass filter portion, and omega high is the 3 decibel cutoff frequency for the high pass filter portion, where omega naught is 1 over the square root of LC. Omega low is negative R over 2L plus the square root of R over 2L squared plus 1 over the square root of LC squared. And omega high is equal to positive R over 2L plus the square root of R over 2L squared plus 1 over the square root of LC quantity squared. And we're also going to have a bandwidth, which is omega high minus omega low, and it will still be R over L. So this bandwidth is telling us the frequencies that get rejected. All right, the last thing then is our phase response. So theta h of omega is the inverse tangent of the imaginary part. So omega RC 1 plus omega squared LC divided by 1 plus omega squared LC squared plus omega RC squared divided by the real part, 1 plus omega squared LC over that same denominator, 1 plus omega squared LC squared plus omega RC squared. And the denominators cancel each other. Sorry, this bit right here should be squared. Yeah. So this cancels one of these, and we're left with the arctangent of omega RC divided by 1 plus omega squared LC.